Welcome to today's lecture on energy measurements in nuclear magnetic resonance, NMR spectroscopy. In this session, we will explore the basic principles behind NMR and how it is used to investigate molecular structures and dynamics. Specifically, we'll look at how proton NMR and carbon-13 NMR are used to study organic compounds. A key focus will be on the differences in sensitivity between proton and carbon-13 NMR signals. Proton NMR is generally more sensitive, making it easier to detect, while 1,3C signals are weaker, which presents certain challenges. We'll also cover strategies for overcoming these challenges when detecting 1,13C signals, such as techniques that enhance sensitivity. Finally, we'll briefly compare NMR with electron spin resonance, ESR, which is another important spectroscopic method, to understand the key differences and when to choose each technique. Now, let's dive deeper into the purpose and core concept of NMR spectroscopy. NMR is a widely used technique to measure the energy required for a nucleus to transition between different spin states within an applied magnetic field. The energy transitions that occur during these changes provide invaluable information about the structure and dynamics of molecules. This makes NMR one of the most powerful tools in structural biology and chemistry. At the heart of NMR lies the interaction between a spinning nucleus and a magnetic field. Every spinning nucleus has a magnetic moment, and when placed in a magnetic field, this moment interacts with the external field. This interaction results in energy transitions, which can be detected by NMR instruments, helping us understand the molecular structure of compounds. Now, let's explore the differences between proton and carbon-13 in terms of their magnetic moments and how this affects their sensitivity in NMR. The proton has a much stronger magnetic moment, with a value of 2.79268. This strong magnetic moment makes protons highly sensitive to NMR, meaning they produce stronger signals. Additionally, protons have a very high natural abundance. About 99.98% of hydrogen atoms are in the form of proton, which ensures that proton signals are easily detected in NMR experiments. In contrast, carbon-13 has a much smaller magnetic moment, with a value of 0.70220, which is about one-fourth the strength of the proton's magnetic moment. This results in weaker signals for carbon-13 in NMR spectra. Moreover, 13C has a much lower natural abundance. Only about 1.11% of carbon atoms are carbon-13. This lower abundance makes detecting 13C signals in NMR experiments more challenging, often requiring specialized techniques or longer acquisition times. Let's now look at how the sensitivity of proton and carbon-13 signals in NMR differs. Proton NMR is highly sensitive, thanks to the large magnetic moment and high natural abundance of protons. The high sensitivity allows for easier and more efficient detection of proton signals, which makes proton NMR a major technique in both organic chemistry and molecular biology. This sensitivity makes proton NMR a powerful tool for studying molecular structures and dynamics, as proton signals are often readily detectable. In contrast, carbon-13 NMR has much lower sensitivity due to the smaller magnetic moment and lower natural abundance of carbon-13 atoms. With only about 1.11% of carbon being carbon-13, this leads to a much weaker NMR signal compared to protons. To reliably detect carbon-13 signals, more specialized techniques are often used. These can include longer scan times or more sensitive instruments to improve signal detection. So, while proton NMR is quick and efficient, carbon-13 NMR often requires more careful optimization to ensure reliable results. Now, let's discuss some of the key challenges faced when detecting carbon 13 signals in NMR. One major issue is the low natural abundance of carbon 13, which is only about 1.11%. This means that a very small fraction of carbon atoms in a sample are actually carbon 13, which results in a weaker signal. The low abundance of carbon 13 makes it more difficult to detect compared to other nuclei like protons. Another challenge is the lower magnetic moment of carbon 13 compared to protons. The magnetic moment of carbon 13 is much smaller, which results in weaker interactions with the magnetic field during the NMR process. This contributes to the lower sensitivity of carbon 13 NMR and makes the signals harder to detect. To overcome these challenges, scientists employ specialized techniques. These can include using higher sensitivity NMR instruments, increasing the scan times to gather more data, or enriching the sample with higher concentrations of carbon 13 isotopes. These methods help enhance the intensity of the signals and improve the detectability of carbon 13 in NMR spectra. Next, let's explore electron spin resonance, ESR, a technique that complements NMR. While NMR focuses on nuclear spin transitions, ESR analyzes electron spin transitions. A key difference between the two techniques is that the magnetic moment of a free electron is about 700 times greater than that of a proton. This large magnetic moment makes ESR significantly more sensitive than NMR, allowing it to detect even very small amounts of free radicals or other unpaired electrons. This high sensitivity makes ESR ideal for studying dilute solutions containing free radicals, atoms or molecules with unpaired electrons. These free radicals are often reactive and short-lived, making them difficult to detect with NMR. ESR's enhanced sensitivity allows it to study reactive chemical intermediates or free radicals that would otherwise go undetected with NMR. As we conclude this presentation, let's summarize the key takeaways and look ahead at future directions for both NMR and ESR. NMR sensitivity. Proton NMR is highly sensitive, making it a go-to technique for analyzing molecular structures. In contrast, carbon 13 NMR is less sensitive due to its lower magnetic moment and natural abundance. This sensitivity difference plays a key role in choosing which type of NMR to use for specific applications. ESR sensitivity. Electron spin resonance. ESR is extremely sensitive, especially when studying free radicals and other paramagnetic species. This high sensitivity makes ESR ideal for investigating reactive intermediates and free radicals, which are difficult to study with other techniques like NMR. NMR applications. NMR finds widespread applications across many fields, including chemistry, medicine, biology, and food science. Its ability to provide detailed structural information makes it indispensable in both research and industry. Future developments. Both NMR and ESR continue to evolve with advances in instrumentation, techniques, and applications. As these technologies improve, their potential for scientific discovery expands, offering exciting opportunities for new research and innovations.